Hi everyone, this is Mr. Hall and this is a quick video about the reactivity series and displacement reactions. This kind of follows on from the stuff which I was talking about with regards to metal oxides, and from here we'll follow into a bit more about redox reactions and so forth in later videos, but hopefully this stuff is relatively straightforward. It's kind of stuff that you tend to do in terms of experiments, so hopefully this can kind of support the stuff you've been doing in class. So the objectives of today's video are to, first of all, to place metals in order of reactivity based on data, and that can be based on what you kind of see in a test or in a table or something like that. The second thing is to explain how the reactivity of metals with water or dilute acids is related to the tendency of the metal to form positive metal ion. I'll talk more about that later because it sounds quite confusing. And then finally, we're going to deduce an order of reactivity of metals based on experimental results, which is quite similar to the first one, but might be put in a slightly different form in the exam question. So there are some subtle differences between the two. All right, so let's get started. So first off, the first thing you have to really think about is what do we mean by sort of metal reactivity? So the way to think about it in my mind is, if you think about metals that you've commonly come across either in the real world or in the lab, if we first think about potassium, you've probably seen the demo where your teacher will get a lump of potassium and put it in water. There'll be loads of fizzing because hydrogen's being released, and you'll see a flame, and it all looks very exciting. So it's very clear that potassium is a very, very reactive metal. Okay. However, if you look at other metals, they obviously don't do the same thing if you put them in water. So, for example, if you look at iron, now if I put an iron nail in water and leave it for several days, eventually you'll start to see it corrode and rust, and you'll see some of the iron oxide, which is the orange sort of substance which gets created on the outside of it. It doesn't happen immediately. It's not like potassium where it goes into flames and so forth, but it does react over a long period of time. And then if you look at gold, which is another example, gold is a very unreactive metal. Doesn't do a great deal if you put it in water. It can stay for sort of hundreds or thousands of years and not do a great deal at all. So we can see on the left-hand side, you've got potassium, it's my belt, which isn't very reactive. Potassium is very reactive, I should say, all the way to gold, which is not very reactive at all. So what you can do is you can put them on a spectrum where you've got the most reactive on the left-hand side, you've got the least reactive on the right-hand side, and then you've got that reactivity sort of as a spectrum going from left to right. So that's just 3 metals out of the many that we could talk about in terms of the reactivity series. Now I could put all these metals into a little table, okay? So I could put potassium at the top as the most reactive, I could put iron sort of in the middle, sort of middling reactivity, and I could put gold at the bottom. And then what I can do is I can do the same thing by looking at the reactivity of lots of other metals, okay? So between potassium and iron, I can fit in sodium, calcium, magnesium, aluminium, carbon, important element to put in this reactivity series for reasons which you'll find out later in your course, and then zinc. And then between iron and gold, I can put lead, copper, and silver, and then below gold, I can put platinum. Now that is your reactivity series, where you've got the most reactive at the top and the least reactive at the bottom. Now, you don't really have to necessarily remember that order. It's quite useful to kind of know basic reactivity trends, in as much as you'll notice group 1, group 2 elements tend to be high at the top because they tend to be quite reactive, and then you should know sort of from experimental experience and what you've done in your classroom that copper's not very reactive, gold's very unreactive, iron's kind of in the middle. Knowing those basics of where they are is actually quite useful when you're doing exam style questions. So the more experience you get, the better. Now, another way of talking about reactivity is the tendency to form positive ions. So what you can say is the more reactive a metal, the greater the tendency for it to form a positive ion. Now that seems quite confusing when you first look at it. And the best way in my mind of considering this is by looking at potassium and sodium. Now you know that from the reactivity series which I've created before, that potassium's kind of quite high up at the top over here. So that is this element over there. And then sodium's over here, which is sort of next down from potassium, and it's second in line. Now, you've hopefully learned from previous lessons that at the top of group 1, the elements are very reactive, and then as you go down, they become less reactive. So at the top of, they become more reactive, I should say. So you've got lithium, and then you've got sodium, and then you've got potassium, and then so on. I think you've got rubidium, and then you've got cesium, and so forth. And then as you go down group 1, they become less reactive, okay? Let's not let me do that. So it becomes less reactive as you go down to here, all right? So less reactive. Oops, sorry. Now, the reason why it's become less reactive is because it's less likely, I'm making a massive mistake here, it becomes more reactive. Now, the reason why it's becoming more reactive as you go down is because of the fact that it's more likely to form a positive ion. Now, if you look at potassium over here, now potassium is lower down group 1. It's a bigger atom, therefore it's much more willing to get rid of this electron in order to form a positive ion, okay, because there's greater shielding, there's a greater distance between the nucleus and the outer shell electron, which means the attraction's a lot weaker and so forth. Now, sodium's a lot higher. It's less reactive as a result, and you can see that from a reactivity series because it's a smaller atom, okay? So the distance between the nucleus and the electron is smaller. It's got a greater attraction between the nucleus and the outer shell electron, so it's much harder for this electron to leave the atom. Now, that logic actually runs through for all of these elements. So if you go to gold, for example, gold is very unwilling compared to the others to let go of its electrons to form a positive ion. So as you go down, it becomes basically that it's got a lower, I'm trying to think of how to word this, it's got a lower tendency to form a positive ion. Whereas up here with potassium and sodium and so forth, they have a greater tendency, and it's as a spectrum. Okay, so that's sort of the basics that you need to know. You need to know about the tendency to form positive ion. You need to know generally that metals form this reactivity series. The question is, how are you actually going to encounter this in exam style question? Now, there's a couple of ways in which they can ask you. Now, the first thing they might ask you is about displacement reactions. Okay, now the important thing that you need to know is that a more reactive metal will displace a less reactive metal in a reaction. So, for example, let's look at magnesium and zinc. Now, magnesium and zinc are at different parts of the reactivity series. Magnesium is more reactive than zinc. So there are two potential reactions that could happen here. Now, let's say that we've got magnesium reacting with zinc sulfate. Now, the sulfate here, to be honest, it could be something else, right? It could be chloride, it could be nitrate, it could be phosphate. It doesn't really matter. It's almost like a spectator ion in this reaction. The key things that we're looking at are magnesium and zinc. So the question is, can magnesium kick out, i.e., can it displace zinc in this reaction? Now, the answer is yes, because magnesium is more reactive than zinc. So what it can do is it can come in over here, kick out the zinc to form magnesium sulfate, and then it will form zinc on its own. So the answer to this is the reaction will work because magnesium is more reactive than zinc, so we'll displace it. Now, the important thing which I've articulated here is that I've mentioned that magnesium is more reactive than zinc. So when you're answering questions like this, making that super clear is really important. And as a result, my products will be zinc and magnesium sulfate. Now, if you look very carefully, all I've done is I've swapped the places of magnesium and zinc. Okay, so magnesium comes over here to form magnesium sulfate, zinc comes over here to be on its own to form zinc, and you can see the products written there. Now, let's say that I reverse this reaction. Let's say I try to react zinc and magnesium sulfate. Now, zinc is less reactive than magnesium. It's lower down the reactivity series, so it cannot kick out magnesium. All right. As a result, reaction doesn't work. Zinc is less reactive than magnesium. Notice I've articulated this quite clearly. As a result, the reaction does not work. Now, in terms of exam style questions, you might get a couple of other things. One of the trickier things to deal with is experimental data, which might look like this. Now, what you can see here is at the top, you've got 4 pure metals. And over here on the left-hand side in this column, what you've got are the different salts, the sulfates. And then in each cell, what you've got is whether the reaction is successful or not. Now, the way to kind of think about this is to think about which metal is able to react with each salt. Okay, so for example, if I look at magnesium, magnesium is able to react with zinc, copper, and aluminium sulfate. Now, what that basically means is magnesium is able to kick out those 3 metals in those different substances. Notice that zinc isn't reactive with zinc sulfate or magnesium with magnesium sulfate because it can't kick itself out, obviously. So if I was to create a reactivity series, I would first off say that magnesium has to be at the top because it's able to kick out zinc, copper, and aluminium. For example, if I was to look at the reaction over here with magnesium and zinc sulfate, it's clear that magnesium plus zinc sulfate, let's write this quite carefully. This reaction is able to proceed Okay, because you can quite clearly see that magnesium and zinc sulfate does lead to reaction, which means that magnesium is kicking out the zinc, which means that magnesium has to be more reactive than zinc. Therefore, my product here would be zinc plus magnesium sulfate. There we go. Now, the next one to look at is to see another metal which reacts with a lot of the metals available. Now, if I look at aluminium over here, aluminium is able to react with the zinc sulfate. It's able to react with the copper sulfate. So that would tell me that aluminium is more reactive than zinc and it's more reactive than copper because it can kick them out in the reaction. But crucially, it can't react with magnesium sulfate. Now that tells me that aluminium is less reactive than magnesium. And we knew that already because if you look over here on the second column here, with magnesium and aluminium sulfate, you'll notice that magnesium was able to kick out the aluminium. So that kind of confirms what we found before. So next in line, in terms of our reactivity series, is aluminium. So now the only two we have left to deal with is zinc and copper. Now let's start with the zinc first of all. Zinc, as we know from our experimental work, it's less reactive than magnesium because it can't kick it out there. It's less reactive than aluminium because it can't kick it out there. But with copper, it does react when zinc reacts with copper sulfate. So if I do zinc plus copper sulfate, that is a positive reaction. It does work to make, I should write sulfate there, to make zinc sulfate plus copper. So what that tells me is that zinc is more reactive than copper because it can kick it out. As a result, zinc must be above copper. So my reactivity series from these four metals is magnesium, aluminium, zinc, copper. So one question you might have to do is to kind of put metals in order based on experimental results like that. You might also have to explain it. So you might have to say, for example, for magnesium, magnesium is more reactive than zinc because there are two reasons why. Magnesium can kick the zinc out in a displacement reaction, and then likewise, zinc cannot kick magnesium out when they try to react with each other. So there's a few ways in which you can articulate it. Now, the other type of problem you might get is if they just show you the reactions themselves. So for example, if I look over here, a classic question you might get is to highlight the reacting metals, deduce the order, and deduce the overall order. So if I look at each one of these reactions, let's start with, I've got some kind of mystery metals here, okay? So I've got X, I've got magnesium, and I've got zinc. And often what they will do is they'll give you letters for elements, because if they give you the elements themselves, it might be a bit too easy, basically, to answer the question, because you might know the reactivity series from what you've remembered. And if I look at the first reaction, I've got X plus magnesium sulfate makes X sulfate plus magnesium. Now, what that basically means is that it's a positive reaction, okay? The reaction does proceed, it does go ahead. Now, because it goes ahead, what it's telling me is, actually I might change the pen color here because otherwise you can't see. There we go. So what it's telling me is that X can kick out magnesium, which means the reaction is successful. That also tells me that X is more reactive than magnesium. So in terms of the order of reactivity for that reaction, I know that X is more reactive than magnesium. So that's my first thing. So if I'm starting to construct it, X is above Mg. That's my first sort of clue, if you like. Let's have a look at the next one. X and zinc sulfate makes X sulfate plus zinc. Now from this, X is displacing zinc. It's a reaction that works. That tells me that X has to be more reactive than zinc. So X is more reactive than zinc. That's my second clue. Now, I know that X has to be at the top of my overall reactivity series. I don't, however, from this, know if magnesium is more or less reactive than zinc. That's my third clue. So for my third clue, let's have a look at zinc plus magnesium sulfate. Now, if I try and react those two together, there's not a reaction, okay? That doesn't work. That means that zinc cannot displace magnesium. As a result, zinc is less reactive than magnesium, or to put it another way, magnesium is more reactive than zinc, okay? And that's my final clue, because then I know that magnesium is above zinc. So if I was to kind of put this together in a reactivity series with all three metals together, I would know that X is at the top, magnesium's next, and then zinc is third. That question comes up quite a lot, so just be aware of that. And that's it. So I hope that's been helpful, and best of luck with your questions with reactivity series.